Hi, today I'm going to be solving a problem where we have two ideal gases, A and B, component A and component B, in a closed capillary tube system where the pressure and the temperature will be held constant. So first in this problem, we have to understand that we have component A and component B divided by a barrier. Well, when this barrier gets removed, these gases are going to disperse throughout this tube. Well, since we have a closed capillary tube, the molar flux of the system will be 0 because molar flux being moles per unit time per unit area in this system, when we have the two things that make up our total molar flux, which is component, the molar flux of component A and the molar flux of component B, well, every time the molar flux goes this way, which is going to be constant area, so wherever it is, wherever the molar flux is right here, it is here, it's everywhere. Well, when this goes, say, positive, this is going to completely counteract it by filling the space going negative. So we have A going up here, and B will come and fill its space. Well, since these are counteracting each other, we know that whatever A is, B is going to be opposite. And whatever B is, A is going to be the opposite in this closed system. So the molar flux of the system is therefore 0. This will come in handy later, but for now we're going to go to the total goal of this problem. Because the total goal of this problem is to relate the molar diffusive component of, or molar diffusive flux of component A, to the mass diffusive flux of component A as well. Well, first we're going to define what the mass diffusive flux and the molar diffusive flux are, so that way we can then relate them with the variables mass fraction of component A, molar mass of component A, and molar mass of component B. So first we're going to define these. So the molar flux of component A is equal to the concentration of A. Concentration of A, let's say what that is the amount of moles of component A per volume. So molar concentration of A multiplied by the velocity at a certain point in this system of component A subtracted by the total velocity of the entire system, the total molar velocity of the entire system, So with this, we're just going to leave this here and we'll come back to it. But these are what these variables mean. And with our mass, oh my gosh, twice in a row. Okay, our mass, what is it? Mass diffusive flux, With our mass diffusive flux of component A, this is equal to our mass concentration of component A. What is mass concentration, you ask? Mass concentration is the mass of component A over the total volume of the system. And this is multiplied by the volume of component A. Okay, wait, we'll stop really quick here. Both the molar diffusive flux of component A and the mass diffusive flux of component A share that they have the velocity of A at a certain point in their equations. Well, that's something we want to highlight because that means we can relate the the molar diffusive flux and the mass diffusive flux. So first we're going to finish off this equation. This is the mass velocity of this entire system. So these are the two definitions of mass diffusive flux and molar diffusive flux. So now going from there, knowing that we have VA, the velocity of the component A in both these systems, we're going to try to relate these two equations. Sorry, we have very little space here, so I'm going to have to erase a couple things throughout this presentation. But if we want to know what VA, the velocity of component A, equals, well, first, let's go back to where we started. We have the molar flux of this system equals 0. Well, we also know that molar flux equals the concentration of the entire system, so that would be the sum of A and the sum of B, which we know is going to be a positive number because we have a concentration A, we have a concentration of B, so these added up together will be a full number. Well, this is multiplied by the molar velocity of the entire system, which, if this multiplied by a positive number, we know that the molar velocity of the system has to equal 0 because this equals 0. So, with that in mind, we can say that this equals 0 in this equation as well, meaning that the molar flux of component A, molar diffusive flux of component A is equal to the concentration of A multiplied by the molar concentration of A multiplied by the velocity of component A at a certain point. Well, that means that the velocity of component A at a certain point equals the molar concentration of A divided by, the molar diffusive flux of component A divided by the molar concentration of component A. See what we did there? So now we can bring this and put it into our mass diffusive flux equation. Exactly. So I'm actually going to erase a lot of the board here because we need a lot of space for this next part. So, you know what? Before I do that, I'm actually going to write this out so I don't lose myself. So we have the mass diffusive flux of component A equals the mass concentration of component A multiplied by the molar diffusive flux of component A divided by the molar concentration of component A subtracted by the mass velocity of this entire system. Well, we are now going to erase up here, and because we have a lot of good things in this equation that we need to go over. So we have mass concentration of A. What's mass concentration of A? We talked about this earlier, but just to remind you, that's the mass of A over the total volume. Well, what is the concentration of A? We would also remember this over, but let's go over it again. So we have the moles of component A over the total volume. Well, when we are multiplying the mass concentration, we're dividing the molar concentration of component A from the mass concentration of A. Well, what we do, we can just draw a nice little division sign here. Mass of A over moles of A, total volume. We can cross these total volumes out. And what does that give us? So we had the molar concentration, or the mass concentration divided by the molar concentration. That's mass over moles, which is molar mass, molecular weight. So we have mass over moles, which gives us molecular weight of A. That's beautiful. Well, molecular weight of A is one of the things that we are trying to put this equation in terms of, to represent the molar diffusive flux between the mass diffusive flux. So this is beautiful. So now that we have the molar mass of A, we're going to substitute that into our mass diffusive flux equation, which is the mass. Mass concentration is already gone. The molecular weight of component A multiplied by the molar diffusive flux of component A. Well, we have a second part of this problem, and we need to really define this here to understand it. What is V? V, the mass velocity of the entire system, is the summation of the mass concentration. Let's see if we can draw it. Mass concentration, because that is representing the mass. How do I say this? That is representing each component's mass over its volume. So each component's mass concentration multiplied by the volume of each component. Okay? So this, the mass, let me take a step back here for a second. So V equals the velocity, the mass velocity of the entire system. So if we're getting the mass velocity of the entire system, then we need the mass fraction, or sorry, the mass concentration of each component multiplied by the velocity of that component. That gives us the mass velocity of each component. But we also have to put this over the mass concentration of each component summed as well. That is just, this is the definition of the mass velocity of the entire system, okay? It's just the summation of the mass concentration of each component times the velocity of each component divided by the mass concentration of each component summed. Well, if we sum up the mass concentration of each component, that actually gives us the density, because then that is the total mass, that's the mass of each component added up over the total volume. Total mass over total volume equals density. So we can just call this density. So what this is, we have what? We have component A and we have component B. So V in this situation would equal, we have, first we don't want to forget about our mass concentration of A. But now that we have this definition down, we know that we need the mass concentration of B. Well, we're going to start with A actually. Mass concentration of A times the velocity of A plus, because it's a summation, of the mass concentration of B, because that's our other component in this system, multiplied by the velocity of the component A at a specific point. Well, this is all over the density as we just mentioned. And now we need to take what we found earlier and make some relationships in our head. So what we had earlier is we had that the velocity of A was equal to the molar diffusive flux over the concentration of A. That is something we defined earlier. That is true when the velocity, the total molar velocity of this system is 0. That is true. And this holds true in this system. So we know that this is still true. Well, what is the molar concentration of A? We discussed this earlier. The molar concentration of A is the mass concentration of A divided by the molecular weight of component A. Because the mass concentration is the mass of A over the total volume of A, right? And the molecular weight of A is the moles over the total mass. Well, so if you see what we do here, we have mass over volume, mass of A over volume, over moles, or actually, sorry. That'd be mass of A over moles of A. Okay, well, what do you do here? You have mass of A, mass of A. So if we multiply this, well, actually, we don't even need to multiply. We can cross these two out, and what's that give us? We have volume over moles, but this is actually multiplied up here. So you get the moles of component A over the total volume. What does that equal? That equals the concentration of A. So we just figured out that the concentration of A equals the mass fraction, no, not mass fraction, sorry. Mass concentration of component A divided by the molecular weight of component A. Well, this is very, very helpful because we're trying to get things in terms of molecular weight, right? So, sorry, I just erased our mass diffusive flux over here, so I want to put that back. But this can get substituted into Ca, giving us two things that we already have in relation to our velocity of A. So we have now the velocity of A equals the molar diffusive flux of, actually we're just gonna do multiplied. So say it was divided by the concentration of A, well, divided by this, so we're gonna inverse that, and it's gonna be the molecular weight of A over the mass concentration of A. That is what the velocity of A is equal to, as we just proved. So, where do we want to throw this in? We want to throw this back up here to our VA. So we're going to erase some things yet again here. I don't want to confuse myself. So now, this mass diffusive flux of the component A is equal to the molecular weight of component A times the molar diffusive flux of component A subtracted by the mass concentration of component A multiplied by this mass concentration of component A and this mass concentration of component A will cancel out. Therefore, we will have just the molar diffusive flux of component A multiplied by the molar mass of component A. Well, now you're saying, hold on, we have the molar concentration of component B and the velocity of component B. Matt, what are you doing with that? We haven't seen that. Well, the great news is, since we defined earlier that since we've defined all of this, let's say that. I was going to go back to different equations, but since we've defined all of this in regard to component A, since these are two ideal gases in a closed fixed system with constant pressure and constant temperature, component B will behave exactly the same way. So we can just sub in this VA. VB will behave the exact same way. So what we're going to do then is we're going to put this, that's equal to VB, which is the velocity of component B. So this will behave the same way. So minus plus, we just said the concentration of the mass concentration of B will go mass concentration of B there. These will equal out, and we will have left the molar diffusive flux of component B multiplied by the molecular weight of component B all over the density of the system, all components. Okay, so now where are we at? We're saying, well, Matt, the molar diffusive flux of component B, that's not one of the things we're looking for, and we don't know what that is. Well, guess what? It's the same as the molar diffusive flux as component A. Want to know how we know this? Because up here, what we talked about earlier, when a particle or some part of the gas of component A moves in this system somewhere, it's not moving and leaving open space where it was. It's not just going to leave open space there. Instead, it's going to trade places with the component B, meaning that the molar diffusive flux of both of these components, of both these gases in the system, will be equal. Well, to make our lives easier, we're going to go ahead and get rid of the molar diffusive flux of component B because we don't have that anywhere else in our equation, and we want to define the relationship between the molar diffusive flux of component A and the mass diffusive flux of component A, so we're going to put this in terms of component A. So now, at this point, we have molecular weight component B, molecular weight component A, we're very close. Now we have to get rid of this density of the system and the density, or the mass concentration of the component A, and get this in terms of mass fraction of A to get it where we want it to be. So we're going to erase all this down here now. And the good thing is that we know that, where are we at? Well, first we're just going to simplify this down a little bit so we can see this easier. So we're going to look at the mass diffusive flux of component A is equal to the molecular weight of, is equal to, what do we have in common? What's a common factor out here? The molar diffusive flux of component A. So we're just going to go ahead and get this out of there, multiply it by the molecular weight of component A subtracted by the mass concentration of component A times the molecular weight of component A plus the, wait, I'm doing something a little off here. This is also mass, sorry, part of my mistake up here. I didn't factor this mass concentration of component A into both sides of the equation. That's why I'm messing up here. So we would actually have the mass concentration of component A multiplied by the molecular weight of component A minus molecular weight of component B divided by the density of this, the density of the entire system. Okay, and here we are. Sorry for my, I just had a nice little, I don't even know, brain fart, if you want to call it, loss of words. So, what is mass concentration? Mass concentration, again, we've defined this a couple times. We will go back. Mass of component A over the volume. Well, if we are multiplying the mass of component A, if we're multiplying mass concentration of component A and dividing that by the density, what is density? Density is the mass of the system over the entire volume. Well, what is that going to give us? Dividing mass concentration by density, I crossed off the wrong thing. Mass of A, the volume will cancel out, total volume. So we'll have the mass component A over the mass of the component system. What is that? That's the mass fraction. WA, which represents the mass fraction, because we have mass of A over the mass of the whole system. So, there we are, giving us this relationship between mass diffusive flux, molar diffusive flux, both of component A, multiplied by the molecular weight of component A, subtracted by the mass fraction of component A, multiplied by the molecular weight of component A, subtracted by the molecular weight of the component B, which gives us this relationship between molar diffusive flux and mass diffusive flux of the component A in terms of the molecular weight component A, molecular weight component B, and the mass fraction of component A. Thank you very much for your time. I hope this helps, and please come back for more videos in the future. Thank you.